When you create a variable of, say, the int type or integer, your variable actually contains the value that you assign to it. That is, when you declare a simple integer variable and assign, say, 10 to that variable, the memory location corresponding to the variable actually contains the value 10. These types are called value types because variables of these types actually contain the values. On the other hand, when you create a variable of a type that is a class, things work differently. Instead of containing the instance of the class, that is, the object that was created from the class's template, the variable contains a reference to the object. So these types are called reference types because variables don't contain objects of these types, they refer to them. Now in some languages, such as C and C++, the reference to an object is called a pointer. In managed languages like Visual Basic and C#, you really don't need to think about pointers, as you do in some of the languages. C# does have tools that you'd need to work with pointers if you really need to, but that's very rarely necessary. Now when you create a variable of a reference type, the variable has a specific value before you assign it a reference to a particular object. Its value is null. You can also say that the variable contains a null reference. Before you can use the variable, you have to assign it a value so that it refers to an object. If you attempt to use the variable before assigning it a reference, you'll raise a runtime exception. Now, you can test to see if a variable refers or doesn't refer to an object using syntax like this: if variable equal null or if variable is not equal to null. Here's some sample code that shows how you can use these tests for null. So the sample creates a customer object, so this is based on the customer class that's part of the project, and sets that initially to null. And then the second statement creates another instance of the customer class, but this time it actually news up a customer object and assigns it a customer ID. And then the code just simply checks to see if customer A is equal to null, and in this case it is going to be null because I'm explicitly assigning it to null. And I write out that message, and then it checks to see if customer B is null, and it's not, so we won't see this message. And then after I print those messages, I then attempt to set the value of the city property for each of the objects. And notice that all of this code is wrapped in a try block, so if there's any problems here, there's going to be an exception that's thrown, and we catch it there, and we just display the message. Now a little bit of a spoiler alert, we are going to have a problem because cust A city equals Los Angeles. Cust A is null. Null objects don't have city properties, and so this is going to cause an exception. But if this line were to execute, which is not going to, then this would execute just fine because customer B does in fact have an object reference, it does have a city property, it takes a string, and so this statement, if it ever executed, would execute successfully. But it's not going to because this is going to throw an exception. It's going to come here, catch the exception. We don't do anything else after the catch block, and so the method ends. So I'll go ahead and run it, press F5. And I'll select the A option, and there you can see that cust A is null. So we got that first message that appeared because cust A is in fact null. This message doesn't appear because cust B is not null, so this code within this if block doesn't execute. And then it attempts to execute this code, throws the exception displays that message, and that's why we see the object reference not set to an instance of the object. Okay, I'll stop that. Now, one thing to note about this is that I explicitly set cust A to null. That wasn't just to make it clear in the code. So if I get rid of that and move off, notice that we have a red squiggly there. And it says that I'm trying to use an unassigned local variable cust A. So the compiler is telling me that I declared this variable, but I didn't initialize it. And that's a problem. We can never use uninitialized variables. And this is something that C# does that other C-based languages don't always do. C in particular doesn't do this. It's preventing me from attempting to use a variable that's not even been initialized. All I need to do is initialize it to null. It doesn't have to have an actual object reference, just a null reference is fine. But it's not going to compile the code if I've not initialized that variable. More specifically, if I attempt to use the variable before I've initialized it. Okay, so I'm going to undo that change there. So I want the code to compile. And so once again, that takes care of that problem. Now we need to talk a little bit about the end of an object's lifetime and what happens within the .NET runtime when an object needs to go out of memory. So the way this works is that the .NET runtime has a feature called a garbage collector, which is often just referenced as GC. And this is an efficient, unobtrusive process. It runs all the time that managed applications are running. And it takes care of reclaiming memory that your reference variables use as they create and work with objects. Unlike code built and run in other environments, with .NET you generally don't need to worry about when an object gets removed from memory. When you're building managed applications, the GC takes care of managing and reclaiming memory for you. So here's just about the shortest possible explanation of what the garbage collector does. The garbage collector monitors memory that your .NET applications use in real time as the application is running. As objects are no longer used by your applications, then the garbage collector reclaims the memory and marks it as being available for use by other objects. Then, sooner or later, as your applications need memory, the garbage collector reclaims the memory. Now, if your computer contains a large amount of available memory, the garbage collector may not reclaim the memory for a long time, minutes more. It's not just something that happens every few nanoseconds, because that could be an impact on performance. It's a very intelligent system that Microsoft has refined and improved dramatically in the roughly 15 plus years that .NET has been a commercial product. Now, the garbage collector can't release an object's memory until it's no longer being used. For local variables, when the method ends, the variable goes out of scope and the garbage collector can release its memory as is needed. For variables that are declared outside a method, you can explicitly set the variable to null in order to exert some control over when the memory is released. And then, when the garbage collector determines that an object no longer has any references to it, sooner or later it reclaims the object's memory. Then at that point, the .NET runtime calls the finalize method of the object, allowing you to run code that needs to be run as the garbage collector removes your object from memory. The trick here is that even if you don't explicitly define a finalize method for a custom class, it has one anyway. Now, the reason that every class you create, and pretty much every class in the .NET framework has a finalize method, is that every class inherits from the base system.object class. And if we scroll down here and take a look at the methods of that class, you'll see that system.object has a finalize method. And so, because every object ultimately inherits from system.object, every object has a finalize method. And that's a key feature in what makes, or what allows the garbage collector to do its job, how it knows that an object is available for garbage collection. Now, if your class doesn't maintain any references to unmanaged resources outside the class, there's no reason to worry about any of this. In that case, when no other code holds a reference to your .NET object in memory that's created from a class, all of its internal resources are removed from memory with the object. So it's pretty simple and straightforward. So that's going to apply to most of the classes. Most of the code that you write are not going to be using any kind of unmanaged resources. The nice thing here is that C# hides that functionality, which makes it easier for C and C++ developers to migrate to C#. Instead of requiring you to override the finalize method, C# lets you create a destructor instead. It's the analogous to a constructor. The destructor method takes the same place in the object's lifespan as the finalize method, but makes it a little bit easier for you. The destructor looks kind of like a constructor, except that you have to precede the procedure name with a tilde character, a little wavy character. On most keyboards, it's the key to the left of the 1 at the top of the keyboard, above an apostrophe. In addition, the destructor declaration can't include any modifiers, public, private, and so on. All right, and so what this does is this essentially takes care of wrapping the finalize method. Now, what's kind of interesting and a little bit confusing about this whole process is that finalize is the method that executes, but you can't directly override object.finalize in C# code. And where it gets confusing is that, again, we're still in the documentation for system.object, and we look at the description of finalize, allows an object to try to free resources and perform other cleanup operations before it's reclaimed by garbage collection. We can look at the documentation for finalize, and we can read the documentation. It says allows an object to try to free resources and perform other cleanup operations before it's reclaimed by garbage collection. It's a virtual method. Method is used to perform cleanup operations. Method is protected and therefore accessible only through the class or through a derived class. That's fine. Describes how finalization works, and so forth. And then we get down to this note here that kind of seems to take everything back. The C# compiler does not allow you to override the finalize method, even though it's a virtual method, which generally means that you have to override it. Instead, you provide a finalizer by implementing a destructor for your class. A C# destructor automatically calls the destructor of the base class. So this is actually the way that you need to, in essence, implement finalize. Okay? So just know that the finalizer method is there. That's what is actually doing the work. But it's essentially behind the scenes. You have to put your custom code into a destructor. So anything that has to happen when this object's being removed out of memory, primarily releasing handles or references to external resources, like a database connection or a file handle or something like that. That's where you need to put the code in a destructor. You don't override the finalize method. And that all actually simplifies things quite a bit, but the documentation is a little bit confusing about it. Okay, so let me get out of here. And here I have an example of testing finalize. And in order to use this, I have a stream demo class. I'll select that and hit F12 to open up the definition of that. And what this does is, this isn't a fully developed class, so I don't have the code within the constructor here. I know this is the constructor because it's named the same thing as the class. I would typically set up the stream, connect it to some sort of stream. I'm using a file stream here, so it's going to be some sort of probably a binary or text file or whatever it is. But I would do all that work here. But here's the destructor. And I know it's a destructor because it has the little tilde prefix on the name. It doesn't have any access modifiers. There's no public or private or protected because you can't use those. And because this is a reference, this holds a reference to an external resource, an unmanaged resource in .NET speak. I need to explicitly take care of closing that. So I check to see if it's null. If it's not null, then I call the close method of that object, and I indicate that I'm within the destructor. So the reason that it's important to have a destructor in this kind of class is that if you keep creating multiple instances of this class within the application, you have to open up a whole bunch of different files, it's possible that Windows could run out of file handles. Now, in this age of 64-bit Windows and higher resources and much more memory, it's a lot less likely than it was just a few years ago to run out of resources like that. But it's always good not to hog resources. Clean up after yourself. All right, so because of that, it's important that the file within the class get closed at some point. And if you don't close it anywhere else, when the object gets destroyed, you should close the file at that time, and that's what the destructor does. Now again, to emphasize the point, you really only need to worry about releasing resources of objects outside the .NET runtime. Managed objects, the ones that are created that are part of the .NET framework library or your own code, generally take care of their own resources, and the garbage collector is very intelligent about doing that. So one example, as I've mentioned, of a resource that you need to be careful of is files, because those are provided by Windows and aren't managed objects. Strictly speaking, we're using the Windows API in order to use the operating system features in order to access different files. And then database connections fall into that same category. So don't worry about adding a destructor to every class that you create. It's really only an issue if you're working with unmanaged resources. And if you're coming from other programming languages where you had to be very explicit about releasing every object, everything that you use in your code, whether it's your custom code or a library you're using or whatever, you're going to find this is a little bit jarring, but it really simplifies your life. You have to write a lot less code because the .NET runtime takes care of all that for you. Okay, let's go back over to program.cs there. And here's a method that tests how this works. So all it does is it creates an instance of the stream demo. So I have an instance in memory. It actually holds a reference to that object in memory. Then I set that reference to null. And at that point, the .NET runtime has the freedom to remove the object from memory at any time. And when it does so, it calls the class's destructor. Now the problem here is that just indicating to the garbage collector that it can remove an object from memory doesn't mean that it will, at least not in the foreseeable future. And that's generally fine for most applications. You can just let the garbage collector do its work when it gets around to it. But for this demonstration, it'd be nice if you could actually see the cleanup code run. And so that's why I included this additional statement here. Again, not something you need to use all the time. It's just that if you want the garbage collector to do its work immediately, then you have a bit of control over the process by calling this collect method of the GC object. Okay, and if I hover over this, you can see that this is actually the name of the class, system.gc, and it contains the system garbage collector, the service that automatically reclaims unused memory. All right, so that's a little bit weird name of a class name in the .NET framework. But anyway, GC is the garbage collector. It gives you access to the garbage collector so you can exercise a modicum of control over the garbage collector. All right, bottom line, it forces a memory collection. All right, so I'll go ahead and run this application again. And I'll test finalize, so I'll select B. And here you can see that we're in the destructor. It actually executed and everything's good and that memory has been reclaimed. In particular, the handle to that file stream that was open to an external resource has now been released and can be reused by some other process in Windows. Now, what's kind of interesting about this is that it took a bit of time for the garbage collector to respond. Sometimes when you run this application, I'm not going to try too many times, but let me try one more time. Sometimes the inDestructor message appears after the press any key to continue. If I run this enough times, we'll get a chance where it hits that, but I'm not going to take the time to do that. And the reason is because this message, the press any key to continue, is invoked or caused by the console menu class well after, relatively, the end of the test finalize method has finished execution. And so the timing of these two is essentially uncoupled. And so the garbage collector, I'm invoking that method. It's not a blocking method, so it just tells the garbage collector to do its thing and then it continues on code executing. If it takes, say, a few nanoseconds or a few seconds for the garbage collector to do its work, maybe there's a complex code within the destructor for that class and it takes maybe a minute to run because it has to clean up a whole bunch of different stuff, then inDestructor could appear after the press any key to continue message. So just be aware of that kind of little timing issue there. Now, I've shown you this technique, but I need to include a warning. Don't call the gc.collect method in your own code unless you have a serious need for it. It can execute slowly, and generally you'll never have a reason to call it. Well, except in demonstration situations like the one I just showed you. But every so often, probably twice in your programming career, you might find a situation, or if you're working with particular kinds of external resources, particularly if you're working in an environment that has very limited memory, you may need to take control of the process. So be aware it's there, but don't